So again, we want to say good evening to everybody and welcome to our webinar on Doppler Radar for severe weather. So I'm Joe Deli Carpini, the Science and Operations Officer, and with me tonight is Rodney Chai, one of our meteorologists. So I'll be describing some of the basics for radar and Doppler radar, and then Rodney will take us through some of the applications, including the new dual pole, or maybe not so new, Rodney, it's been about 10 years, but some of the dual pole applications. There's been a lot of new research that's gone into using these dual pole products. So Rodney will be presenting some of that tonight. So just to start, weather radar has actually come a long way. If you want to check out on YouTube our Radar 101, we talk about the history of it a little bit, going back to World War II. But on the left is the older radar system that we had, which was the WSR 57 radar. That's from the 1950s. And then we also were supplemented with the WSR 74 radars in the 70s. And those were the two main radars used by the Weather Service up until the mid-1990s when the Doppler radars came on board. And on the lower right there, you actually can see the radome. This was the New York City radar, which was atop the what is now I believe, the GE building in Rockefeller Center, but it was located in Midtown Manhattan. And for us here in southern New England, we had a radar out in Chatham, Massachusetts, and also another one in Windsor Locks at Bradley Airport and in Worcester as well. So today our Doppler radar network looks like this. You're probably familiar with the area radars. We have KBOX, which is the Taunton radar. And yes, it's still in Taunton, even though our office is in Norton. To our west, we have the Albany radar, which is KENX. That is actually located in East Bern. That's why you get the ID of ENX west of Albany. And to our south, we have the New York City radar, which is on Long Island in Brookhaven. It's KOKX. But you can also see we have a number of other Doppler radars throughout the Northeast, anywhere from Caribou to Gray, Maine to Burlington, Vermont, Buffalo, Binghamton State College, and Fort Dix in New Jersey, which is outside of Philadelphia. So the reason they're located here is because they provide the best coverage across our region from radar to radar. That's how the radar locations were chosen back in the 1990s. So viewing the radar data in the office, originally in the 1990s, we had something called the PUP, which was the Principal User Processor, and this was the workstation. It was two screens, and you had a kind of a mouse pad with a mouse, and you would just click on different products to view them. There weren't as many available as there are today. We just had the reflectivity, velocity, and precipitation products, things like that. So not much to look at, but the problem was only one person could use it at one time. It was very difficult to have more than one person kind of looking at the radar data. It was not the easiest thing. So today, on the right, we use our AWIPS workstations. We can create all different ways to look at the data. Multiple people can look at the data at one time. This is an example of a 4-panel showing reflectivity and velocity and the correlation coefficient. And I'm trying to see what that is at the bottom. It's lightning. So we can really kind of create our own displays to kind of view the data the best way that we want to. So definitely a lot more flexibility today than when the WSR 88D, which is the Doppler radar, came out in the mid-1990s. So let's talk a little bit about radar here. First is the VCPs. Now, back in the old days with the radars, we had to manually, they would rotate by themselves and we would manually scan up and down for different thunderstorms, but that's all automated now. So it automatically scans the atmosphere, completing what's called a volume coverage pattern. And you can see examples here on the left and the right. So the volume coverage pattern, or VCP, it consists of making multiple scans of the atmosphere over different elevations. So on an evening like tonight with no precipitation, we're now in clear air mode. So there's fewer tilts and it moves a lot slower. So it's a lot more sensitive to picking up things like sea breeze fronts, birds, bats, bugs. We can see all sorts of things like that. And for another example, this morning, we had showers and thunderstorms moving through. So we were in precipitation mode. That gives you more tilts and the radar spins a little faster. So we'll get through some of the VCPs here in a minute. But those are the two basic ones that we have: clear air mode, which is slower moving, fewer tilts, and precipitation mode, which is more tilts and rotates a little bit faster. So let's take a look at some of the VCPs that are available here on the WSR 88D. Hopefully this will catch up in a second. I think my internet might be a little slow, Rodney, so stand by. There we go. So we've got three different VCPs that we mainly use. On the left is the clear air, and that is VCP 35. And it takes about 2 minutes for each elevation. So it's relatively slow. And a complete volume scan of these levels takes about 10 minutes. And you can see an example on the lower left. That's actually snow. We didn't have too many examples of summertime clear air. So that's one we can use for snow to detect snow a little bit better. In the middle is our precipitation mode, VCP 215. That's a little bit faster, about 1 minute per elevation, and more scans, as you can see, up to about 19.5 degrees, so you're scanning a lot higher. But notice there's a few gaps here as we get up near the top. This will do a complete VCP in about 5 to 6 minutes, and an example is there on the bottom of some showers and thunderstorms near our south coast. And then finally on the right is VCP 212. That's our severe weather mode. That rotates a lot faster. It's about 30 seconds per scan for elevation. And notice we filled in a lot of the gaps here up near the top. So we're getting a more complete scan of the atmosphere. That takes about 4 to 5 minutes for a full volume scan. But we can get the base scans, meaning the lowest level, 2 to 3 minutes, or even as little as 1 minute. And I'll show you some enhancements we have for VCP 212 when we get into severe weather. And hopefully this will update again quick. I apologize, things are going a little slow tonight. So we have what's called dynamic scanning, and hopefully our slide will update. Here we go, let's see. Oh, it's a little slow. There we go. So we have dynamic scanning in VCP 212. There's 3 different things that can be used. The first one is called AVSET, and it automatically ends a volume scan when the coverage of precipitation is low. So in other words, if there's less than the 30 dBz level, which is essentially where you start to get showers, and the 18 dBz thresholds are met, it will end the scan. And in other words, it won't waste time scanning where there's nothing going on. So this is an automated algorithm in the radar that helps save time. It'll start a new volume scan instead of wasting time where there's nothing going on. Now we have 2 manual scans we can employ. The one we use most often is called SAILS, and it stands for Supplemental Adaptive Interrogation of Low-Level Scans. So what it does is it will add 1, 2, or 3 extra base scans at the half degree, this lowest one, every 1, 2 minutes, or for the most part. So SAILS 3 is the most. You'll get the new scan every minute. And that's important when we get into things like tornadoes, because it gives us a 1 minute scan at that lowest level where typically our tornadoes occur. So it really helps the forecaster get that extra data instead of having to wait 4 or 5 minutes like we typically would in VCP 212. And then similar to that is what we call MERLI, which is mid-level rescanning of the lowest elevations. And that's similar to SAILS, but it covers the lowest low and mid-level scans as shown here. So it's covering not just 1, but the 4 scans, half degree, the 0.9 degree, 1.3, and 1.8. So this isn't something we've used too often, but I think we're going to try and use this a little bit more. This is useful when you've got storms a little bit closer to the radar as opposed to long distances. So we're going to maybe try that one out a little bit more. But for the most part, folks in the office will at least use SAILS to add those lower level tilts. And that's most useful, not just for tornadoes, but when we've got severe weather at longer ranges, maybe out near, for our radar, out near the Berkshires, for example, or over the coastal waters south of New England, where we want to see those lower level scans a little bit more. So again, we have AVSET, which is automatic, SAILS, which is manual, and then we have our MERLI, which is manual as well. And we've got some guidance on which, to use for what situation. There's really no, silver bullet or rule that works every time. But for different weather events and based on distance from the radar, we can employ different strategies. So pretty much MERLI or SAILS we use for the tornadoes. Closer to the radar, we're going to use the mid-level where we get more of those higher scans. And then farther out from the radar, we're going to use SAILS more often, where we just really need that low-level scan because the higher ones are going to overshoot everything. Similar situation when we've got organized damaging wind. So think of things like squall lines with wind damage and cold pools rushing out, microbursts, that sort of thing. Very similar. When we get into hail and just heavy rain, typically it's SAILS 1. Although we had some research out of MIT Lincoln Labs that showed for flash flooding, SAILS 3 was actually better. It provided better rainfall estimates. For landspouts, meaning kind of those almost fair weather type of water spouts or those weak funnel clouds, We're using Murley at short distances and the sails at a little bit longer. And then for microbursts, it's kind of a mix of all of them. We typically use sails in sails 2 for severe weather, but you can also use 2 or 3 depending on the situation. So just some of the guidance that we use. Again, there's really no single answer for any given situation. It's up to the forecaster based upon maybe chatting in the office and kind of seeing what the biggest threat is that day. But we do have many options available to us when we get into VCP 212. All right, so let's start talking a little bit here about some of the radar basics. And we reviewed this in Radar 101, but we'll just go through it again just to tell as a refresher. So the radar velocity, remember, it's Doppler radar because it determines the movement or phase shift of the particles. So think about like a train horn coming toward you. You notice the tone changes, or a siren will change as the vehicle passes you. It's the same thing with Doppler radar. It's measuring a phase shift of the particles, which can be aligned with kind of wind. So we have base velocity on the left. Those are ground relative winds. So we use that a lot for things like microbursts or straight line winds. And on the right is storm relative motion, which is rotation within the storm. And that's just the base velocity subtracting out the storm motion. So it's the motion relative to the storm itself. And as you probably know, anything with kind of the greens, that's our standard for motion toward the radar, and the reds are motions that is away from the radar. So we'll take a look at just an important thing to remember here is the radial component of what's being measured. So the radar is not always giving you a true measurement of velocity. It's very important to remember that. So it really depends on the viewing angle. So sometimes we'll use multiple radars to kind of look at what's going on. An example is over Connecticut. If storms are moving to the east, the Taunton radar or Albany radar would have a better view than the New York City radar on Long Island because it's almost perpendicular. And you can see here, this shows you how much wind is detected based upon the angle. So at a 0-degree angle, in other words, the storm is coming right toward the radar, you're going to be able to measure about 100% of the wind. But note that drops as you get about a 50-degree angle, you're only measuring about 65%. And when you get to a 90-degree or perpendicular, you're not measuring anything. So again, that example over Connecticut, a storm moving west to east through Hartford, from the OKX radar to the south will really not be measuring any of the velocity at all. It'll be perpendicular to the beam. So you have to be careful when you're watching a storm. If it gets perpendicular to the radar beam, you're going to lose the velocity data. Sometimes people think that's the storm weakening, but it's not. You're just measuring less of the wind that's actually out there because of the angle. So that's an important concept to remember. So I'll show you an example here of what the best sampling is. And this is what we call down the radial. So think, for example, you're looking at these storms. This was over Providence in Rhode Island in August of 2015. Notice the radar here off to the right. It's pointing pretty much straight down at the storm, and the storm is moving to the northeast toward the Taunton radar. So these winds that you're seeing are going to be very accurate. Near Cranston and Warwick, we had 70 to 80 knots of wind, which is over 80 miles per hour. Down here near Westerly and Stonington, we had the radar measuring 60 to 70 knots of wind, which is close to, again, that's 80 plus miles per hour. So we did have a gust here in Charlestown of 83 miles per hour, which was pretty close to that 70 knots. So it's telling you, the velocity data is good when you've got what we call right down the radial or a 0-degree angle from what you're measuring. Now, again, as an example, anything from Woonsocket or Attleboro moving east is going to be measured very well. But a storm that's maybe from Newport going toward, say, somewhere Fall River, New Bedford, you're going to lose the velocity data in this area because it's becoming perpendicular. So when we interpret velocity, we've got different patterns to look at. And there's two basic ones. One is convergence, which is air that's meeting up. We've talked about that in many of our case studies. So in this case, the radar is here in the black dot. Notice you've got reds, which are winds that are away from the radar. But on this side, you've got green, which is wind toward the radar. And this is the boundary here that's outlined in the black line. This is a zone of convergence. So you're seeing air that's meeting up. It's going to be lifted up. And often this can be a sign at the higher levels of storm strengthening. So that's what you want to look for. Or it's simply just storms advancing along. There's good convergence. That means they're going to keep on going. They're not going to weaken. Now, on the opposite side, we've got divergence. And this is an example. The radar is here in the middle at these crosshairs. You've got greens toward the radar, and you've got reds that are away from the radar. So this is a divergence couplet, it's called. And this is a case where you might see a microburst or a gust front, something like that. So it doesn't have to be severe. It can be, but in this case, the winds are maybe around, I think, 20 or 25 knots. I figure 30 miles per hour, so nothing really severe, but it's showing that there's divergence. The storm is probably, the downburst has occurred. The downdraft is pushing out colder air, so the storm is probably just about done. An example of a microburst, and we see this all the time here in southern New England, but this was a good one, was back in July of 2019. We had a microburst in Longmeadow out in western Massachusetts, and we were able to use a radar out in UMass Amherst. They have what's called a CASA radar. It's a smaller system, but it's a more localized radar network that they operate. They've got one in Amherst and also a number of them in the Dallas-Fort Worth area where they're conducting research. You can see it at this address here on the website, or just search UMass Amherst CASA radar. It shows clearly that this was a microburst, and we actually had some reports of downed trees in the area. Someone had thought maybe it was a tornado, but without having to take a trip out there, we were actually able to look at the radar data. You can see a bit of a bow here in the line, kind of punching south, and clearly here we've got a microburst. So the radar is up to the north. You can see we've got these greens here. There's a little bit of convergence as air is moving away and toward, but this is a gust front essentially, and air to the other side is moving out. So the storm definitely produced a downburst, and that's what caused the damage in the area. So we were able to pretty much clearly say with a lot of confidence that this was a microburst and not a tornado. So when we interpret velocity, obviously the thing we want to look at is rotation. And there's a couple things that we look at. A simple rotation pattern, yes. And again, it depends where the radar is. So I'll start here. In this case, the radar is down to the bottom of the picture. You've got reds that are away, greens that are towards. So you can imply there's a counterclockwise circulation here. Now, it's always important to note the elevation and the depth of the circulation, how broad it is or how tight it is. In this case, you can see that the reds are right up against the greens. So that's what we call gate-to-gate shear. It's against outbounds, right against inbounds. Sometimes you'll see there's a little bit of separation. That's a little bit more of a broad circulation. So that's not necessarily indicative of a tornado, but it can be too. So that's something you want to look at. It's always important, is there depth in it? Is it just at the low level? Does it go up a little higher? A lot of our tornadoes here are just at the lower levels, but some of them will go up a couple of scans. You might see the 0.5, 0.9, and the 1.3. But that's important to consider. Also, persistence in depth and in time. Is it a very transient feature? We know a lot of our tornadoes are down in a minute and back up. But in some cases, the longer lasting ones, say like Revere back in 2014, Revere, Mass. That one was a little more persistent. But we call it tight and bright. So you want gate to gate, you want strong values of inbound, strong values of outbound. Now, the one thing we calculate is called rotational velocity. So that's here on the left. In that couplet, you take the absolute value of the inbound wind and the absolute value of the outbound wind and divide it by 2. So an example would be you've got 30 knots of inbound and maybe 40 knots of outbound. So you add the two together, that's 70, divide by 2, you have 35 knots of what's called rotational velocity. And that's what we use in our tornado warning decisions, at least as part of it. We look at the strength of the couplet, the rotational velocity. We look at the depth of the rotation and also the persistence. Is it something that's gone in one scan? Is it something that's holding on? And obviously the stronger the rotation, the tighter the rotation, the more likely it is you're going to have a tornado. So when we use velocity information, it really helps us also visualize what's happening within the storm. So this is a little confusing, but I think everyone in the audience has got enough background, they'll understand it. So on the right is just a typical supercell that we're looking at diagram. You don't have to worry about all the arrows and everything, but the bottom line is you're looking at air coming in, inflow. It goes up within the storm, forming the updraft. You've got outflow up at the top, and then you've got the rain-cooled air forming the downdraft. And the boundary of that, you can get a mesocyclone, you can get a tornado. But we can see the same structure here on the radar slices here on the left. So we're going to start at the lowest level. This is the half degree. And we have what's called cyclonic convergence. So again, the radar is off to the lower part of the image. So we've got strong inbounds here, strong outbounds here. They're not gate to gate, but they're close. So this is called cyclonic convergence of a pattern. If we go up a little bit higher, now we're at the 1.8 degree scan, and this could be a couple thousand feet. Now we've got pure what's called cyclonic rotation. Note we're more gate to gate, greens against reds, and you can see how we have the counterclockwise circulation. As we go a little bit higher in the storm, maybe now we're up at about, I don't know, 8 or 10,000 feet. This is the 3.1 degree scan. Still have that cyclonic rotation, very similar to this. So we know we have a lot of depth in the storm. Could be several thousand feet in that case. And then up at the top, this is up at the top of the storm, the anvil. Notice we've got a divergent pattern. So we've got air rushing toward the radar, air rushing away from the radar. And this is up at the 10 degree elevation. This could be, easily 30,000 feet. But this is a strong signal for divergence. And why this is important is the stronger the divergence at the top of the storm, or the stronger the air is rushing out, meaning you have to be forcing more air to come in to replace it. So think about it. If you're getting rid of all the air at the top, pushing it away, you've got to bring air up to replace it, just to conserve. Essentially, you're conserving momentum and things like that. So the stronger the divergence signal, that means the more severe the storm can be. And there's actually some correlation between storm top divergence and hail size, for example. So this is very useful. But looking at all these velocity couplets together, you can really get a sense of what's going on within the storm, kind of on a 3D level. All right, so I'm going to begin looking at some types of storms, and then I'm going to hand it over to Rodney. So let's start with our pulse storms. And these are your garden variety type storms. They maybe last 30 minutes, 45 minutes, and then they kind of collapse. These are your typical summertime storms that don't do very much. In this case, notice we've got a few microburst signatures. This was, I believe, out of the St. Louis radar. We've got a couple of storms right near the radar. Notice the one to the northeast has winds coming toward the radar and away. This is a microburst. Not necessarily severe. It's only about 20 to 30 knots. And into the south, right south of the radar, we've got another signature here. You've got air moving in and air moving away. So it's a quick way to kind of see if storms are going to weaken, or what the strength of the gust front will be. That's useful not only for severe weather, but we use it for our boating community if we're putting out a special marine warning. We use it all the time for our aviation forecasts. So think about Logan Airport, TF Green, Bradley, Bedford, among others. If there's going to be a wind shift, that's very important to their operations. So looking at the velocity data can help us give them a little bit of lead time to anticipate a significant wind shift. And then the next version are the multi-cell storms. And in this case, we're looking at what's called a QLCS, which is a very organized line of storms, or a quasi-linear convective system. So this was the example from May 15th of 2020. We also had one in October of the same year. These are those long-lived lines of storms that can go 80, 100 miles or beyond and bring widespread damaging winds. So this is looking off the Albany radar. You can see we have reflectivity on the left and velocity on the right. Typically, the hazards with these are straight line winds, and usually the higher end wind speeds, 70, 80 miles per hour. Occasionally, we can have embedded tornadoes under the right circumstances, and even flash flooding behind it. Notice we've got this initial line, but there's a lot of heavy rain also behind the main line of storms, which can bring flooding once that initial line moves through. So with that, we're gonna get into a little bit of research. Rodney's gonna take it over from here, and this is what I was talking about. This is some newer research that's been out the past couple of years that's been done within the Weather Service to kind of identify where the threats are with these QLCS type storms regarding damaging wind, tornadoes, and flash flooding. So Rodney, I will hand it over to you at this point.
Well, thank you so much, Joe, and good evening, everyone. So this slide is a little bit heavy, but I'm going to break it down for you. So basically what you're seeing here is, this is called the 3 ingredients method. Basically, issuing someone, even in this case, we're talking about massive vortices, massive cyclones that are, potentially precursors to producing tornadic storms. And so the three ingredients, briefly, they are: firstly, you want to make the balance and slightly shear dominant region. Secondly, low line normal 0 to 3 kilometer shear is more than 30 knots. And finally, locate bows and local surges. So let's break it down. First, So there are a few acronyms that for you. So UDCZ, that's basically your updraft, downdraft convergence zone. So recall Joe talked about 3D thunderstorm graphic. So there's a, for a storm to survive for a long time, it needs a constant supply of energy. So that's your updraft. But it also has the downdraft as well, as where it basically, releases energy and you feel that cool breeze, a surge of air at the surface. That's your downdraft. So where they converge is called a UDCZ. So once again, updraft, downdraft convergence zone. And so you can usually locate this UDCZ using the basically the lowest scan, 0.5 degrees, storm relative motion, SRM, velocity, and your spectrum width product. So most of you probably would be familiar with SRM and V product at 0.5 degrees. So what is spectrum width? Spectrum width is the distribution of, so think about like a river. So when you have turbulent flow, that's basically you have high spectrum width values because you have kind of like high distribution of velocity. And then on the flip side, when you have kind of like smooth flow of a non-turbulent flow, that's your low spectrum width. So the second part of this first factor is you want to compare the location of the UTZZ to the updraft region in the 0.5 degree reflectivity product. And here there are three types of locations. So shear dominant, balanced, and cold pool dominant. So you can see where Joe is pointing. So in the middle, that's your balanced regime, and then to the north, that's the shear dominant, and then you have the cold pool dominant regime to the south. So basically, when you have cold pool dominant, your UTZZ is out ahead of the updraft tower. So basically, it's almost like the best forcing is kind of like surging out ahead of the storm itself. And then on the other hand, UTZZ is within the energy for the storm to feed on and maintain its strength. We'll move on to the second factor. So locate regions where the 9.3 kilometer bow shear is more than or equal to 30 knots. So basically the shear, remember, so the bow shear, this is something you can get from the SPC metal analysis website. And typically we want to, for storms to become severe, we want 30 knots bow shear. And then secondly, you use the equation. So in this case, you have delta U, that's your line normal 0 to 3 kilometer bow shear, equal sine theta, and then M is your 0 to 3 kilometer bow shear. So basically, that's why it's so important when we have severe weather events, we would start up because we would have someone focus on the metal analysis. Just not looking at the radar, but just the metal analysis. And this is why it's so important, to kind of get a good sense, what value is the bow shear, and then you use this simple equation to determine the line normal value. And one thing is that this is especially true for the northern portion of the Boeing segment. This is where the local surges and bows often change the orientation of the UDCZ. And then finally, you have the third factor. So you locate the bows and local surges. So the rear inflow jet or outflow are more likely to cause a local surge or bow. And you want to look for the Mach signature. So basically, that you want to look for the rotation at the upper levels, in this case, the 8,000 to 16,000 feet. So you look at your 1.3 degrees, and so on. You try to look at the upper elevations of the storm to look for those rotation. And also the low level velocity, storm relative motion, and spectrum width can also reveal developing local surges faster than the reflectivity. So this goes back to is it a cold dominant, cold dominant, or shear dominant? So so those are the three ingredients. There's a lot, but if you can kind of master this, then you have a pretty good sense of the storms. So let's look at a few fall panels. So to orientate you, so the top left, that's reflectivity, top right, storm relative motion, bottom left, spectrum width, and bottom right, velocity. So you can see we labeled for you on the slide. So you can see in the middle, that's the balanced regime, and to the north, the shear dominant regime, and then to the south, where the cold pool has surged ahead of the updraft towers, that's your cold pool dominant regime. So what does, so basically what happens after you identify the regimes using the three ingredient method? So basically, this again, these are the same four panels, but we have highlighted the threat that you should be focusing on. And because different parts of the storm, in this case the QLCS, is associated with different threats. So in the middle, where you have the more balanced regime, you have the wind or embedded tornado threat, but mainly it's a straight line damaging wind, although you couldn't rule out an isolated spin up within the line, especially if there's a break in the line. And then for the shear dominant, that's where you have to be concerned about. Okay, that's the tornadic threat is high. So as a radar operator, I would talk to my meso analyst. So which part of the storm is shear dominant, which part of it is cold pool dominant, because the cold pool dominant part would be associated with the flash flooding, right? Because this is where you're going to have the training storms because of the cold pool, because you can allow for the heavy rain to be trained at the same locations over a prolonged period of time. So that would increase the flash flooding threat. So and typically if we have a higher end event, there will be someone focused on the severe threat. So in this case, that would be the damaging wind, tornado threat, and hail as well, of course. But there will also be someone who's focused on the flash flooding potential. So in this case, clearly, if you have cold pool dominant regime, you would have to think about potentially issuing flash flood warnings. So I know this is a very busy diagram, but I'm just going to highlight some aspects of this diagram for you. So I talked briefly about the line break. So that's again towards the top central part of this graphic. So basically, when you have a line break, you have to be on the lookout for tornado threat, and this is usually where and this will be typically located within the balanced regime, but it's neither cold pool dominant nor shear dominant. So because QL, typically the main threat is staying straight wind, because it's a linear storm in a sense, but because it's quasi-linear, so this line is going to kind of like break in certain locations, and these are the locations where you have to be on high alert for a brief spin up. So and typically how we warn this kind of storm is that we would issue a severe thunderstorm warning. We would add a tag that a tornado is possible, and if the tornado threat does indeed materialize, then we would issue a tornado warning for this kind of storm. So And then the other thing is, okay, so we talk about tornado. If you look at the bottom right corner, these are the confidence builders for us to issue a tornado warning. Because the tornado warning activates the wireless emergency alert, not something we want to, issue indiscriminately. So we take, we want to build our confidence by looking at the 0.5 degree reflectivity, storm relative motion, correlation coefficient. We see that it's indeed the debris from the tornado, as well as the differential reflectivity. So I think I can move on. So this is a real life scenario. This was the October 7, 2020 QLCS, and again, it is the main threat from this was the damaging straight line winds. And I remember this event, we had like widespread 70 to 70 miles per hour wind gusts. And but being a QLCS, there was that isolated tornado. And actually, this graphic was courtesy of the science and operations of the from there, because his relative live in Millis. And so he gave us this graphic here, and you can see basically where there's a line, kind of like a line break as well. And if you compare the storm relative motion couplet with the reflectivity, you notice that there's actually a curve. So that's actually kind of almost like a hook echo signature that you want to see, for tornadic storms, and then you compare it to the velocity product. Indeed, there's a line break, and there's actually almost a type rotation, but it's very localized. And in the grand scheme of things, you would have to be very focused to notice that curve in the reflectivity and that localized rotation on the velocity product. But there was a brief tornado, and we were able to confirm it during our storm survey. So I mentioned the hook echo. So basically, as the name suggests, there's a hook on your when you look at the reflectivity products. And this typically happens in a supercell environment. Especially the central part of the country, they get a lot of supercells, but but there are a few times, like in the Springfield, Mass 2011 tornado, we actually had a supercell environment. It's almost like the Great Plains environment migrated to Massachusetts. And so in this case, you can see, where the inflow of the storm is and the rear flank down drop. And again, this is a very healthy storm, and that was able to last a long time. And the Springfield, Mass 2011 tornado was actually a long track tornado. So you definitely need a supercell environment for not just brief spin-offs, but a tornado that's on the ground for quite a bit of time. So once again, this is the Springfield tornado. It was rated as EF3 following storm survey, and you can see, that's the reflectivity process, unmistakable, hook echo, and then you can see that just that tight and bright rotation, where the green. Remember, the green is that basically inflow velocity, and then velocity, and down velocity. So you can get that counterclockwise circulation, and then you also see that purple and blue within the green. That's basically indicating very high values. inbound velocity. And so now remember that our radar is to the east in Taunton. So this is looking out towards the Connecticut Valley. Now, a word of caution. So it doesn't mean that when you see an Hooke echo on the reflectivity product, doesn't mean that it's always a tornado. So in this case, this is August 2015, and you can see. I mean, if I were to just give this radar composite to you without telling you the location, you would think, oh yeah, there's a tornado on the ground, maybe a long track tornado. But if you look carefully, this is near Gardner, which is in central Mass. Now remember where our radar is. It is in Taunton, Mass. Now you're talking about, maybe 70 miles to the west of sampling at 1,000, and that estimate is talking about 500 feet elevation. So, this is at best indicating a mesocyclone at 7,000 feet above sea level. So, if you're just relying on this, your tornado warning will be a false alarm. And so it's important to know your environment. You need to know the low level profile. So as Joe alluded to earlier, so our radar technology has just improved leaps and bounds in the last 2 decades. And one of the biggest advancements in the radar technology, and I will tell you, from what I know, I mean, not all countries have this technology. This is the dual pole radar, vertical dimension. That's why it's dual pole. And as a result, we are able to get information about the horizontal and vertical profile, as well as the size and shape of our atmospheric targets.
Apologize if this is slow or if your audio is cutting out. I think we're having a few internet connection issues here, but we'll try and keep going.
We'll try our best. So this is the correlation coefficient. Basically, it measures the uniformity of the hypermeter atmospheric targets. So a value of 1 indicates basically uniform profile. So if you get 1, that's basically straight raindrops or wet. And as the value decreases, so when you get to 0.9, that could be indicating hail, graupel, or a wintry mix. And then when you get to 0.85, 0.8, you're talking about large hail. So, and then if you get to like 0.75, it could be tornado debris. So, the lower the values, but sometimes you have to be careful because, there might also be birds or insects, especially in the summer, because just doesn't mean it is raining. It just means it's non-atmospheric targets. So differential reflectivity, on the other hand, tells us about the shape of the target. So in this case, you can see it is, from negative to 0 to positive. And so for raindrops, if you have, large positive value of ZDR, that's increasing raindrop size. For large hail, that's basically you want to have a negative ZDR value. And then for snow, dry snow would have, a low but positive ZDR value, and then once you get to a greater positive value, that's wet snow. Now, ZDR can be very useful, not just at a single level, but actually at a kind of, this is what we call it, you look at the atmosphere at different tilts, and using the ZDR product. And so you can get kind of like a three-dimensional visualization. So in this case, the ZDR column, especially in the lower levels, can identify updrafts and new cell location, whether they're splitting or filling in the line. So another application is the ZDR arc. So this basically side spotting, and this can reveal potential for increasing low-level rotation. So you want to, the clue here is you want to look for the high gradient. So you want to look, kind of compare your reflectivity product, which is shown on the top, and you want to look for where there is kind of like a sharp drop off in the reflectivity, and then compare it to the ZDR product and look for high ZDR values. So that's now remember, we always want to build confidence before we issue tornado warning. So this is one of the confidence builders for identifying potential tornadoes. So on the topic of tornado debris signature, TDS. So again, this is again a four panel. So you have the reflectivity top left, some relative velocity, some relative motion on the top right, differential reflectivity bottom left, and correlation coefficient on the bottom right. So in order to have radar confirmation of a tornado on the ground, in other words, you have indication of the breathing lofted into the atmosphere, you must have basically a combination of the following: high reflectivity, the velocity couplet tight and bright, and low correlation coefficient. And the bonus is to have low differential reflectivity values. So in this case, whether it is negative value or a small positive value, that would be up. So this, and actually on the K, and so the one, and this was a use the four panel to build our confidence on a potential tornado on the ground. So if you look at the circle right over West Yarmouth, so you have activity. So okay, so and the correlation coefficient. Finally, you have the end-rod, and this is one of the another derived product that the higher value indicates higher rotation, but in a word of caution, you never want to use end-rod by itself without the other product. High value end-rod does indicate a tornado on the ground, but
Rodney, can you hear me okay?
Yeah, I can hear you.
Okay, yeah, we lost some of the audio there. I apologize. But yeah, just the basic point again was the high reflectivity with the velocity couplet and the somewhat lowered CC. Notice it's not in blue, but it's lower. So that was a case from the Cape Cod tornadoes in 2019. I think we lost a little bit there. I apologize for that. Having all sorts of internet issues tonight, but we'll go on to the next one.
So this was pretty recent, actually. So this was actually November 13, 2021, one of the late season tornado outbreaks. That they actually had dozens of tornadoes on Long Island and then into Connecticut and Rhode Island. So this was actually in coastal Connecticut near New Haven. And so there was an EF0 tornado. And basically, when you look at this radar, you wouldn't think that it's a tornado ground to remember on them. But remember, looking at this office radar, which is on Long Island. And so we are sampling at almost a 90-degree angle from the radar. So with the velocity data being sampled is actually much lower than reality. So as you can see, it kind of look kind of pretty unimpressive on the velocity product on the top right corner. But you can clearly see the lower CC on the bottom right. Okay, so once again the same day, but over the vineyard. So so in this case, you can see we had a tornado warning over the vineyard, and basically it's a potential water spout approaching the island. So that's why we went ahead to put up the tornado warning, and you can see that you have that velocity coupler on the top right corner, and remember the radar is to the northwest, and high reflectivity on top left, and also the lower CC on the bottom right corner. So you would think, it's over the ocean. What kind of debris can it be spinning up? So it's potentially sea spray. We're not entirely sure, but there was enough clues to push the button in this case. So yet another derived product is the specific differential phase, KDP. Basically, it's an indicator of the liquid water content sampled within the beam. And you can, basically the use of this in severe weather warning is that it can be a precursor for downbursts. So, in this case, some of the typical values of KDP, which is in degrees per kilometer, are in this case rain could be really just really any value from slightly negative to very positive. Hail, if the values increase, it means you're transitioning from dry hail to wet hail. And then same thing for winter in snow. Dry snow has lower KDP values. Wet snow has higher KDP values. So yet another application is the three-body scatter spike. So the telltale sign for TBSS is, so notice where the circles are. So notice how you have a kind of almost like a tail of lower reflectivity going southwest from the hail core. So the hail core is unmistakable. That's those purple values on the reflectivity product. It's very high reflectivity, indicating the hail core, but then you have the tail of lower reflectivity moving out away from it. That's your three-body scatter spike, and it is a clue for big hail in the storm. And the reason for that is because the radar beam bounces off the large wet hail, and it is being returned to the radar at a weaker weaker, energy or velocity. So that's why you have that, tailing off the reflectivity, and it produces a black hole that extends out from the storm. But it is useful to identify hail in this case. So range folding is actually a challenge for us in radar operations. So, for those of you who, who may live in the Connecticut Valley or towards Western Mass, you're kind of in the, zone, almost like the zone of silence, because you're kind of almost equal distance between the Albany radar and Arbor radar in Taunton, Mass. And typically, the radar is pretty good out to, I would say 145, 150 miles. But if we're trying to sample something that is a little beyond that, now bear in mind from Boston to Great Barrington is about 150 miles. So if you want to sample something in Western Mass, you might get something called the range folding or the purple haze. In this case, you can see that purple arc on the velocity product. Now, this is something that is non-desirable because, what if you are sampling something that is being impeded by the purple haze? So, one quick way to get around this is to switch to a different radar, but this doesn't guarantee removing the purple haze. And this is basically indicating range-folded radar data. Basically, the radar works by emitting energy, to the atmosphere and then hitting hopefully what is an atmospheric target and then bouncing back. But it takes time. Obviously we're talking about, a very short time range here, but it takes time to come back. But before coming back to the radar, you already emit a different beam of energy. So you might cause interference, and this is why you get the purple haze. And in more scientific terms, this has all to do with the radar's PR, power position. So, so what do we do? Radar sends out pulses of energy to detect the product. So, you would always run into this dilemma where you want to sample as long a distance as possible, but it will come at the cost of range folding because it takes time to turn to the longer the distance, the longer the time it's going to take for it to come back, and you increase the likelihood of basically the beams interfering with each other. So yet another, this is almost like a cautionary tale for using the dual pulse technology. This is called a side lobe contamination. So basically, when you emit a beam of energy, you have to think about emitting kind of three-dimensional lobes of energy. So you have the main lobe, and then on the side you have the side lobe. So can occur in vertical or horizontal direction. So this is an example of, so we have reflectivity actually over California, and remember the beam rotates clockwise. So in this case, the side lobes actually hit the higher reflectivity core and return to the radar as higher reflectivity, but then the main lobe and the main beam of energy is actually hitting the lower reflectivity area. So as the radar operator, you have to be cognizant of potential side lobe contamination, because you might be thinking you have a stronger storm than it actually is in reality. So it might be a stronger storm in higher elevation, but it has not translated to the surface. So in this case, you have to be aware of what elevation this higher reflectivity is. If it is 7,000 feet, I mean, it might be a prelude to a microburst require material like this. So in this case, you have to be situationally aware so that you don't get by potential site of contamination. So in this case, this is an example of over Sudbury mass in 2020. So to the left is 0.5 degree reflectivity. To the right is 6.4 degree reflectivity. So for Sudbury mass 6.4, you're talking about over 10,000 feet elevation. So if you just look at the right image, you might think, oh, that's the pretty intense storm over Maynard and North Sudbury. But in reality, if you look at the lower reflectivity, not so much. I mean, it's actually over South Acton, so quite a bit of difference here. And and this is where having experience helps, because now if you have worked through different storms, sometimes things just don't make sense, and this is where you have to really lean on your experience and double check to make sure that in this case, when you're in doubt, always compare to the 0.5 reflectivity. So if you just look at the storm relative motion product on the left-hand side, you would think maybe there's a storm approach. But if you look at the reflectivity, this case doesn't make sense to have a tornado on the ground. So
reiterate, sorry, we were a little choppy again with the audio. So what it's doing is it's taking this half-degree SRM, and this is actually aloft at that 6.4. It's falsely mapping it to the lowest level. So it looks like a tornado, but that's why you compare it. There's no reflectivity, so it can't be real, if that makes sense.
So yeah, for more information, feel free to go to the warning decision website. This is the website. If you don't remember the whole URL, just remember. Also search on YouTube. TR region, TWIP. There will be a lot of useful videos. So yes, I'll pass it back to Joe for Q&A.
Yeah, and again, apologies for the audio issues. I think it's an internet issue, maybe on my end, Rodney. So I know it was a lot of material too. So I don't see any questions right now. I hope everybody, if you don't get it, you're going to get a chance to look back on YouTube again, or certainly ask me any questions if there was something you didn't quite catch because of the choppiness. So again, sorry about that.